Now that we know how to differentiate power functions, the next logical step is to look at polynomials, which are just combinations of power functions. Each term is a constant times a power function. And it turns out that this is not very difficult to do, but we need a few rules for differentiating functions here. Bong! Now, there's a couple of things we need to write before we deal with these rules. So if C is a constant, we need it to be a real number, and F and G are differentiable, then the following rules are true. And I want to read these out so that we're all on the same page. So this first one says, if we have the derivative of a constant times a function, we can just take the constant and multiply it by the derivative of the function. So basically, we can take a constant and pull it out of a derivative when it's a constant multiplier. We also have these two rules that say that the derivative of a sum or a difference of two functions is equal to the sum of the derivatives or the difference of the derivatives. These rules are going to be really helpful when we're differentiating polynomials, because a polynomial is going to be sums and differences of individual terms that are constants times power functions. So we're going to be able to use these rules to break down polynomial functions into individual terms and use the power rule pretty easily. I want to prove one of these rules for you. I want to show you where these come from, because it's important to know why these rules exist, especially because sometimes there's a thing that you might think is going to be true, but it's not going to be true. So we do need the ability to prove or figure out whether or not a rule is actually true. So what I want to do is I want to show you where the sum rule comes from. I want to prove that. And so what we're going to do is we're going to let capital F of x be equal to lowercase f of x plus g of x. So we're saying this function capital F of x is a sum of two functions, and we're going to assume that those two functions are differentiable, just like we are in our rule. So if we want to know the derivative of capital F of x, that's going to be the limit as h approaches 0 of capital F of x plus h minus capital F of x all over h. Now, because capital F as a function is defined to be the sum of two other functions, we can actually replace capital F of x and capital F of x plus h in this problem with our other functions. So capital F of x plus h is just little f of x plus h plus g of x plus h. That's because capital F is the sum of those two functions. And then we have to subtract capital F of x, which we know is just little f of x plus g of x all over h. Now, what I'm going to do is I'm going to distribute that subtraction to each of those terms. But to make life easier, we're also going to do some rearranging. So we've got the limit as h approaches 0 of, I'm actually going to break this into two different fractions. Let's do this. So what we're going to do is we're going to look at the f's and the g's separately. So we've got f of x plus h minus f of x, because when we distribute that subtraction, the f of x becomes negative, all over h. And then if we look at the g of x terms, we've got capital G of x plus h minus g of x, because again, that subtraction getting distributed causes that g of x to be negative all over h. And we know that the limit of a sum is equal to the sum of the limits so long as those limits exist. So we can split this up into the limit of f of x plus h minus f of x all over h, plus the separate limit as h approaches 0 of g of x plus h minus g of x all over h. And we recognize these to be the individual derivatives of the functions f prime of x plus g prime of x. Those are just the limit definitions of f prime and g prime. And so what we've done through using some different operations and some limit laws is we've shown that the derivative of a function that's equal to a sum of two functions is equal to the sum of the derivatives. So this is the second rule here. The derivative of a sum is equal to the sum of the derivatives. We could similarly show the other ones are true using similar methods. Now that we have these rules, I want to go through one derivative together. Let's differentiate, and I'm going to use d over dx here because it's going to be helpful notation here. Let's take the derivative of 3x to the fourth minus 6x cubed plus x squared. All right, let's differentiate this polynomial function. Now, we've got sums and differences here, and the rules say that if we have the derivative of a sum, it's the sum of the derivatives, and if we have a derivative of the difference, it's the difference of the derivatives. So we can actually, I'm going to do this in one step, but it's really two steps. We can look at this first bit plus the second bit. This is the sum of two different functions, and so when we're differentiating, we can split it up into the sum of the derivatives. But then we can also split this one up, because this is the difference, so it's going to be the difference of the derivatives. So if we apply these rules all together, this is going to be the derivative of 3x to the fourth minus the derivative of 6x cubed plus the derivative of x squared. And then we can use this first rule. The derivative of a constant times a function is just the constant times that derivative. We can pull the constant multiplier outside of the derivative, and we're going to do that with the first two terms here. So this is going to be 3 times d over dx of x to the fourth minus 6 times the derivative of x cubed, and then we still have plus the derivative of x squared. And now if we look, all of the functions that we need to differentiate are power functions, so we can use the power rule in each of these. So we've got 3 times the derivative of x to the fourth using the power rule is 4x cubed. Remember, the exponent goes out front, and then the new exponent is decreased by 1. Then we've got minus 6 times the derivative of x cubed is 3x squared. And then we've got plus the derivative of x squared is 2x. And then we can go through and multiply those out. 3 times 4 is 12, so we've got 12x cubed minus 6 times 3 is 18, so we've got 18x squared, and then plus 2x. And this is our derivative of the original polynomial function that we had. I've gone through and shown each step how we use these different rules, but once we get used to this, we can do things a lot more quickly and simpler than that. If we want to differentiate this polynomial, we can just say, well, the derivative of x to the fourth is 4x cubed, and when we multiply 4x cubed times 3, that gives us 12x cubed. Then minus the derivative of x cubed is 3x squared. 3x squared times 6 is 18x squared. And then plus the derivative of x squared is 2x. So in the end, we are going to get to the point where we can do all of these derivatives without showing all of these steps. I'm justifying each of these steps for you right now because I want you to understand which rules we're using and how they allow us to work with this. But in the end, we want to get to the point where we're comfortable enough with these rules that we just go through and do the derivatives quickly and painlessly.